Okay. So I thought before I prove the Cauchy integral formulas, um, which is these formulas that will give us, the key to the kingdom, that tells us the value of the function, holomorphic function, and also its nth derivative, provided that it's holomorphic on some open set containing some closed disk, with the center Z naught. So before we prove this, um, I want to establish something because we're gonna need this. We're gonna need this so that it will be helpful for us. So what have we shown so far? We showed Cauchy theorem, but sort of in a restricted sense, right? So we have Cauchy, where this consequence is that if f is holomorphic on open disk, then for any closed curve in this open disk, this closed loop integral is 0. So maybe I'll add a little closed loop like that. And also that if you're holomorphic on an open set U that contains a closed disk, then the integral along this boundary is also 0. And certainly every closed loop inside. But what about an arbitrary loop in an arbitrary open set, right? That f is holomorphic on. And so that's what I would want to discuss. So the general idea is this, that if f is holomorphic on some open set U, and you have two curves that are homotopic with the same endpoints, meaning that we can continuously deform one curve to another while fixing the two endpoints, then the value of the integral will be the same. So that's what I want to establish by only using what we have established so far. So let's see if that's possible. Okay. So let me write down what is it that we have. So we showed, so far, the story so far. So we showed a couple things. One is Gorsatz. So we have FTC as well. So we have the following. Okay. So far. One is fundamental theorem of calculus, okay, for complex analysis, for complex analytic functions, which is saying that if f is continuous on U, some open U, and f has a antiderivative, has a primitive on U, and f has a primitive on U, namely some function big F on U such that the derivative of f is equal to little f on U. Then, for any curve, and remember we said we define curve as piecewise smooth, right? For any curve, gamma, say, I don't know, this in U, let's say gamma 0 is the endpoint A, gamma 1 is the endpoint B. So it's a curve that joins points A and B. The integral, the contour integral, well, not contour, but the line integral of f over gamma joining the points A to B is this big F of B minus big F of A, right? So this is just fundamental theorem of calculus, very reminiscent of the usual calculus one, but we just evaluate at the endpoints. So this is existence of a primitive. Okay. How was this proved? How was this proved? Well, if you have a primitive, right, this just reduces to the real version, right? So we apply the definition of what it means to integrate over a curve, by parameterizing this curve with some piecewise function z of t. And then we'll realize that it just reduces to the real version of fundamental theorem of calculus. So we know this fact, okay? So, and an immediate consequence of this corollary is this, is that if f is continuous on some open U and f has a primitive on U, then for any closed loop, closed curve, the integral will be 0, because then we just have the endpoints subtracting each other, then it's 0. So the corollary to the fundamental theorem of calculus is that if f is continuous on some open U and f has a primitive, so this is O if primitive on U. So if you have both of these, then for any closed curve, gamma, okay, we have the closed loop integral around gamma of f of z dz is equal to 0, right? Okay, so this is FTC. Now this hinges on f having a primitive, okay. 2, we also established Gauss-Sachs, right? Gauss-Sachs theorem for triangles. And what does this say? This says if f is holomorphic, meaning complex differentiable at each point, and I don't require the derivative to be continuous, just complex differentiable, okay? Holomorphic on U, some open U, such that U contains some triangle T and its interior in the sense that in the area inside, not the interior of the set in the topology sense, but the geometric sense, the inside. So, and it's inside, I guess if that's even a word, I of t, I will use, use different notation, I of t. Then the closed loop integral around this triangle of f of z dz is equal to 0, right? So we have some function f that is holomorphic, which is, again, for us, I'm only requiring this to be complex differentiable at each point. Meaning the limit of the difference quotient exists at each point. Okay, and so if you're holomorphic and it contains a triangle, this triangle T and the stuff inside, then this closed loop integral around this triangle, it will be 0. And how was this proved? Remember, this is proved by sort of chopping this triangle into smaller and smaller triangle, and then estimating or writing the first order expression of f near this common point that lies inside all these nested triangles. So this is Gauss-Sachs, and it seems pretty limited, but it was able to prove the following fact: this notion of a local existence of a primitive. Which says this, right? So if f is holomorphic on an open disk, okay, So I don't care what this open disk is. Let's say you're holomorphic on this open disk D. Then, really using the geometry of a circular disk, we can show that a primitive exists in this disk. Then F has a primitive on D. So that was cool. And the idea is, we just calculate, right? If I want to calculate the derivative, we propose what this antiderivative is, right? So the idea is we propose, so if Z naught is, say, a point in D, we propose big F of Z equal to integral of Z naught to Z as in a straight shot, like that. A straight line segment from Z naught to Z of F of WDW as the antiderivative. And to calculate this, to show that this indeed works, you just take the difference of F of Z and F of Z plus a little h or something, and you're going to get triangles, and we use Gorsats to prove this, right? So the existence of a primitive. So we propose this to be a primitive. And it's called local existence because, say you are holomorphic on an open set, then at each interior point there is some open disk around it, and we know that on that open disk there's gonna be an antiderivative. Okay. So this is kind of nice. It's kind of nice. And with this of course shows that, well, if you are if you're holomorphic on open disk, then any curve inside, any closed loop inside will integrate to 0, right? Because you have an antiderivative, so by fundamental theorem, closed loop integrals will be 0. Okay. So what I want to show now is a notion of curves that are homotopic to each other, and their integrals, their curve, it should be the same. Okay. So maybe we could actually call this for homotopic principle, homotopy principle, homotopic principle, I don't know, whatever you like to call it, doesn't matter. Sure, homotopy principle. So what I want to show possibly is the following. Okay. If F is holomorphic on some open U, and curves gamma 0 and gamma 1 are homotopic, fixing the same endpoints, in U. Okay, so we have some open set U, draw bigger. Okay, so we have two curves. Maybe this is gamma 0 and this is gamma 1. And they fix the same endpoints A to B. Okay, so it's homotopic in the sense that you can continuously deform this gamma 0 into gamma 1. So what does that mean? i.e., there exists a continuous function, continuous map f from, so the curve, let's say the domains of the curves are 0 to 1 or something. 0, 1 cross 0, 1 into u, such that, maybe we put this t and s, such that f of t of 0, so initially it is gamma 0 for all t, f of t of 1 is equal to gamma 1 of t for all t, and it's continuous, and for each s, f of 0 of s is equal to a is a constant, which is equal to gamma 0 of t, gamma 0 of 0, which is equal to gamma 1 of 0, and f of 1 of s is equal to the point b, which is gamma 0 of 1, which is equal to gamma 1 of 1. So the endpoints are fixed. Okay. So, this is perhaps some gamma s, right? They continuously morph to this gamma 1 like that. Okay, so if you can do this morphing, this homotopy between these two curves, this deformation of this curve into this another curve, completely inside u, right? There's always inside u like that. Then what I would claim is that the contour, the line integral over gamma 0 and gamma 1 are the same. Okay, so what's the idea of proving this? Well, a couple things. The idea is we will show that for each curve that is nearby, there's some gamma s, such that s is close to the previous gamma s. So if two curves are close enough, within some reasonable distance, not arbitrarily close, but within some distance, then the value will be the same. Okay, so let's see. Proof. Gotta use different color. So here are some ideas. So because we have some continuous f, big F, that's this homotopy, and it's defined on a compact set, the image of f is compact. Of this, basically it's the image, the collection of all the points traced out by all these curves as gamma 0 morphs into gamma 1, right? So the image of this homotopy big F is compact. Okay. And because why? Because F is continuous on a compact set. Okay. So this is compact, and it's inside an open set U. So just like before, I claimed that we can actually cover this this F with some small open ball. So there's some sort of bubble around this image. Okay. And say this the radius of this bubble is some epsilon. Okay. So that's this is just outline for now. Okay. So 2 is that there exists some epsilon greater than 0 such that the ball, the open ball, bx epsilon for each x in the image of F. This is the image. Is contained in U. Okay, so let me write it like this. So there exists an epsilon such that the open ball such that for each x in the image of F, the ball of around x with the radius epsilon is in U. And the proof is very similar to well, the one where I said that a closed disk is inside some larger open disk that is inside some open set. And it's really similar. So I claim there is this epsilon. Okay. So we have this homotopy. Maybe I just draw it like this. This is the point A to B like that. This is gamma 0. And this is gamma 1. So imagine the intermediate curve sort of just goes from left to right like that, just morphs. And so the whole thing, you know, this is the image of F, right? This whole thing that it traces out, you know, this shaded thing is, well, assuming this is the path that it takes, that's the image of this F. And the intermediate curve is some gamma S. But, you know, this is all inside some U, right? And so I claim that, you know, for each point there is a tolerance epsilon, such that if you draw an open ball of radius epsilon around each point, it's gonna be surrounded. It's gonna be inside U. Okay. Next step. So if this is not convincing, then you will need to sort of prove that. Then notice that because F is continuous on a compact set, it is uniformly continuous on that compact set. The compact set being 0, 1 cross 0, 1. So since big F is continuous on compact sets 0, 1, 0, 1, F is also uniformly continuous on 0, 1 to cross 0, 1. So what that means is you can find some delta such that if the two curve parameters are within delta, then the two curves are close by to each other. Okay, so that means there exists a delta greater than 0, such that if S1 and S2 is less than delta, then then what? then gamma S1 of t minus gamma S2 of t for each t, so this is the same t, is less than some epsilon over 3 or something. Okay, for each t. Okay, so I have to think about this. Right, does this make sense? Probably. Right, because, well, what does it mean, right? This means that I fix this thing, then, yeah. This is possible. Okay. So this is saying that so long as 2 points are within, 2 S1, S2 are within delta, then the corresponding pair of points, they are within epsilon over 3 of each other. Okay. So that is to say, if this is gamma S1, this is gamma S2, and S1 minus S2 is less than delta. Then for the corresponding points, so let's say this is some T1, T2, T3 like that. Really, gamma S1 of T1, etc. Then this distance right here, the joint distance I'm drawing these 3 line segments, each one is less than epsilon over 3. Less than epsilon over 3, less than epsilon 3, less than epsilon over 3. Okay. So what? Right, so what? Well, let's fix this S1 and S2. That is less than delta. Okay. Fix any S1, S2 such that their distance is indeed less than delta. So we do have the situation. So the idea is I'm gonna cover the whole thing with some open disk. So because gamma S1 and gamma S2 that are continuous on 0, 1, them themselves are uniformly continuous. So since gamma S1 and gamma S2 are both uniformly continuous on 0, 1, there exists another delta. Let's call this delta tilde. This is for totally different purpose. Delta tilde is greater than 0. Such that if T1 and T2 are less than this delta tilde, then I can make this simultaneously happen because I just choose the lowest delta. So gamma S1 of T1 minus gamma S1 of T2. This is less than epsilon over 3. And also gamma S2 this is also less than epsilon over 3. So I can make this partition. Okay. So now what I would do is I will pick these points evenly. So pick some points T1, T2, T whatever, M, some points, such that the adjacent points Ti minus Ti. Okay, so I'll do this. Pick T1, T0 to be 0, less than T1, less than T2, less than less than some last point T big M is equal to 1, such that the delta T's, the successive difference, so Ti minus Ti plus 1 is less than, I don't know, delta tilde over 2. This just forces this to turn on, right? Okay, so now what happens here? We have these two curves, and now we have picked these points, these time points. So these time points give you these corresponding points on this curve, right? So we have this point 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, something like that. Okay, and this first one, this is at time 0, which is T0. This is at time 1, which is Tm. This is some T1, T2, T3, T4, etc. T1, T2, T3, etc. Right? Now the value of this evaluation, of course, this is gamma. Let's say this is gamma S1 of T1, gamma S1 of T2, right? And similarly down there, right? So we have these points. Okay, so this gives two sequences of points. In the order, so maybe this is gamma S1. This is gamma S2. Gamma S1 of T1, gamma S1 of Tm on the curve of gamma S1, and gamma S2 of T1 gamma S2 of Tm. Okay, so this gives two lists of points. Okay, and the first point is A, this endpoint A, the other one is the endpoint B. Okay, in this order. So what is the relation between any of these points? Well, they satisfy the following property. Between the points T0 to T1, because of the distance is less than delta tilde, the T's is less than delta tilde, the points is less than epsilon over 3. So each segment, the points along, this consecutive segments like that, the distance is less than epsilon over 3. Okay, and going across, because we're evaluating the same point over here, their distance is also less than epsilon over 3. So what does that mean? So for every 4 points, so we have the situation like this. Okay, draw a larger like this. Okay, and there are just too many values, so maybe I call the top value alpha 1. So call these two lists of points, call these points of 1 dot 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 dot. Let's just call it Z1. Z good? What about P? All right. P1 dot 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 PM and Q1 dot 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 QM. Okay. So between PI and PI plus 1 and QI and oh shit. I also want to make sure I can cover them. Wait, does this cover everything? So actually I want to put the points T's so that if I go along, it will cover the whole path as well. Okay, so slight modification. What do I want? So perhaps so we know that this delta tilde exists. So let's cover these paths with balls of radius epsilon over 3 and we have to hope that the points, the t's, are also less than delta tilde. Let's see. So if I cover it, oh, okay. So first I cover it, and then if there is any gap that is too big, I fill it in. Yes. Okay. So slight modification. So what we're gonna do is this. Okay. So it's just slight modification. Okay. Consider the open cover. So again, the image, so note, the images of gamma S1 and gamma S2 are compact. Okay, so I can cover them with small balls. So cover, so consider the open cover of the form B BT BT epsilon over 3 not BT B gamma S1 T of epsilon over 3. Okay, when T is between 0 and 1 for the image of gamma S1, and likewise an open cover b gamma s2 of t epsilon over 3 t between 0 and 1 for the image of gamma s2. So first make this open cover. And so because they're compact, by compactness, there exists a finite subcover. So there, I can extract a set of t's such that these open balls around these t's will cover the O path with balls of radius of epsilon over 3, right? So by compactness, there exists open subcovering. So this gives a list of t's of ti's such that b gamma, a finite list, right, of ti's such that b gamma s1 ti epsilon over 3 covers the image of gamma s1, and likewise for gamma s2. Okay, so we have two lists of t's. We will join them together. Okay, so we'll combine these two lists. Okay, and we're gonna add in extra t's if their distance is bigger than delta tilde. So we'll combine these two lists and add in extra t's such that we get a list t1 dot 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 tm with the property that the distance between successive t's is less than delta tilde over 2 or something, which is less than delta tilde. Okay. And of course, because a sublist covers the whole thing, and b gamma sj of ti epsilon over 3, index over I, go from 1 to m, covers the curve gamma sj, the image of gamma sj, right? Okay, so now let's go back to this picture. So what have we accomplished? So this gives two lists of points. Two lists of points, okay? And so this is what I call, P1 dot 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 PM and Q1 dot 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 QM, where PI is equal to gamma S1 of TI and QI is equal to gamma S2 TI. Okay, so we get these two lists of points such that, all right, such that what property do they satisfy? Well, such that this is PI, this is PI plus 1, this is QI plus 1. First of all, the distance between PI and PI plus 1 this distance is less than what? Well, these are the two image points between the t's, and the t's are less than delta tilde. So we know by uniform continuity over here that if the two t's are less than delta tilde, this is less than epsilon over 3. This is less than epsilon over 3. Okay. Similarly for the q's. Okay. Also, the corresponding points across, this is less than epsilon over 3, and this is less than epsilon over 3. Like that. Okay. So what? So what is if I draw a ball around pi of radius 2 epsilon over 3, this will include it will cover what, right? It will cover the points pi for sure, right? It's in there. It will cover the point qi for sure. It will also cover the point pi plus 1. And it will also cover qi plus 1. Well, why is that true? Right? Well, because the distance between pi and qi, a triangle inequality, right? This is less than or equal to the distance between pi and pi plus 1 plus the distance between pi plus 1 and qi plus 1, each of which is less than epsilon over 2, sorry, epsilon over 3 and epsilon over 3, right? So this is less than epsilon, 2 epsilon over 3. So we'll cover these 4 points. Okay. And does it also cover the open ball and bpi 2 epsilon over 3 covers or contains the open balls bpi epsilon over 3, obviously, and bqi epsilon over 3. Okay. So why does that matter? Well, it matters because okay, so let's see, right? So what indeed. So because if some point w is in bqi epsilon over 3, then the distance between w and pi is, again, triangle inequality, w to qi plus qi to pi. W to qi is less than epsilon over 3, And qi to pi, well, qi to pi, remember that was epsilon over 3. So 2 epsilon over 3. So it is in this. Okay. Now why does this matter? Well, remember the balls around with radius epsilon over 3 along the pi points and the qi points, they each cover, they form a covering of the image of these curves. So what I'm trying to say is these open balls will cover the whole path, basically. So conclusion. As bpi epsilon over 3, bqi epsilon over 3 form open cover for gamma s1, gamma s2. This ball bpi 2 epsilon over 3 will cover both paths. Okay, as well as, these points. Okay. All right, so this is the open cover. I go from 1 to m will cover both. And with the following property that bpi 2 epsilon over 3 covers the points pi plus 1, qi plus 1. Okay, so I'm just doing this very carefully, So let's say we have this situation. So what does that mean? That means first one, I have a ball right here. This will cover these 4 points. There are 4 points here because this point is doubled. Then the next ball over here, it will cover the next 4 points. Okay, so I'm going to draw so that's not really centered, but I'm just going to draw it schematically so it's cover these 4 points. And I want to draw in a way so that these balls cover the whole thing. Okay, and the next thing, it's going to cover the next 4 points. And the last one, it covers the next 4 points. Again, this is 2 points really over here. So we have this situation, okay? We have a sequence of balls that covers both paths simultaneously, and they cover both, 2 sets of endpoints at each time. Okay, so this is just the detail part. Now, we will show that these 2 integrals are actually the same. Now, why I'm so insisting on the balls is that because we have the local existence of primitive, right? So this is what? This is step 4, overly long step 4. Step 5. Now we will show that, over gamma 1 of FCVZ and this gamma S1, gamma S1 and gamma S2 are fixed right now, are the same. Okay. So on each ball, okay, so notice, as F is holomorphic. Oh, by the way, these balls, right, because they have radius 2 epsilon over 3, which is less than epsilon. That's significant because this epsilon was chosen in the beginning that this whole thing is fit inside U, right? So notice on each bpi 2 epsilon over 3, is in U. So F is holomorphic on BPI to epsilon over 3. Okay, great. And what does that mean? So we know it has a primitive on this ball. There exists a primitive F on BPI to epsilon over 3. So that we know. Okay, so we have some F. And if I want to integrate along the curve from BPI, right, we just add them, we just take the difference, right? Okay. Now, between two of these balls, each ball there's a primitive, and because they overlap, what we can conclude is that they differ by a constant. Okay, so we're gonna fix two consecutive balls right now. Let's just call this ball BI, okay? Or yeah. Okay. So let's look at the ball BI and BI plus 1. Okay. So, and let's call the primitive Fi. Okay. So call BI to be this ball of BPI 2 epsilon over 3. And the primitive on BI Fi. Okay. Right. So what? Because they're the primitive of the same function. Right. They should differ by. Right. Okay. Okay, so let's do this carefully. So we have something like this. This is some BI. This is some PI plus 1. This is PI, PI plus 1, PI plus 2, QI, QI plus 1, QI plus 2. Okay. We have some Fi on here, and we have some Fi plus 1 on here. So on the part that they overlap, okay, because they differentiate to the same function on this overlap, it must mean that they are up to a constant, at least on this overlap. Okay. So what that means is the value. So on their overlap, of BI and bi plus 1, which contains the points pi plus 1 and qi plus 1, we must have fi plus 1 of pi plus 1 minus fi of pi plus 1, the difference of these 2 points, which is a constant, equal to fi plus 1 of qi plus 1 minus fi of qi plus 1. So we gotta have this, okay? So as fi and fi plus 1 differs by a constant on the intersection. I don't know about the rest, but on an intersection which contains these 2 points, it must differ by a constant because they're differentiate to the same function, right? They differentiate to the function f as, d fi prime equals to f equals to fi plus 1 prime on the intersection. And now we know that if the derivative are the same on the open set, then they are, maybe we should prove that separately, but that's what we have. Well, why do we care? Well, we care because the value, right, of those. So this is quite important, so we'll box this. The value of the integral around gamma s1 of f of z dz by fundamental theorem of calculus, right? It's just, it's this. It's a sum of fi of pi plus 1 minus fi of pi, right? This is, this is the first segment, and then the second segment, and so on. So we just add it all up. Okay. And what does this tell me? Okay, so if you write this out, you get something like this. F1 of P2 minus F1 of P1 plus F2 P3 minus F2 P2 plus F3 P4 minus F3 P3 to the last one. The last one is the M piece, Fm. P I guess it ends at P1, P2, P3, P3. So the last point is Pm. So this is m minus 1, Right? We just use the n-1 circle. That suffices. Right, this last one will include these four, this include these four, this include these four. Right. So we really just have balls to be a -1. Right. If the last one is demanded to be 0, right? Okay. So we have this minus fm minus 1 p n-1. Okay. So now let's see. Perhaps we can recognize something. Something minus something, p2 minus fi pi plus 1. So this is if the index are the same, minus this is 3 indexes are the same, 1 less. 1 less. So which 3? So I believe we have f2 p2 minus, so this right here, okay, can be converted to q's. So all this thing across like that, can convert them to q's. So this is equal to f1 q2 minus f1 p1 fm minus 1 pm minus fm minus 1 qm minus 1. Now we're gonna demand that p1 and q1 are the same. So I don't think I did that earlier, but I intended to. Here's my list of points. Right. So this gives 2 lists of points where this is A, this is A, this is B, this is B, like that. Okay. And right. Yep. And so all of this is the same. As sum. So this is going to equal to f1 of q1, and this is equal to fm minus 1 of qm. And so this just equals to the sum of fi qi plus 1 minus fi qi, which in turn equals to gamma s2 of f of z dz. Okay, so what this shows, all of this shows that if s1 and s2 are within delta away from each other, then the true curve will have integral the same. So finally, last step, step 6, divide the unit interval 0, 1 into, or partition, partition the unit interval 0 to 1 into 0 is equal to some S1, which is less than S2, less than dot 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 dot, SL, doesn't matter, equals to 1, such that SI and SI plus 1 has distance less than delta. So let's call this S0. So what this means is that the integral between gamma Si of f of z dz will then equal to gamma Si plus 1 f of z dz. And this is for all I. And this is saying that the first one, gamma of 0, which is S0, f of z dz, will be equal to all these intermediate curves to all the way to gamma 1, which is the last one. So we have all these curves. Gamma 0 to gamma 1. If the s's are less than delta, then the curves will have the same integral. And so we establish this homotopy equivalence. So done. Okay, so this is a pretty long proof, but it's quite useful, this homotopy principle. That if you have f as holomorphic, to which we did use, because we used the fact that there is existence of local primitive, right? And the existence of local primitive, again, depends, we use Goursat's theorem to prove it. So this gives us this very nice homotopy principle that if f is holomorphic on some open set U, then the path integral between two curves that are homotopic fixing the two endpoints, same endpoints, will be the same. Okay. And we're gonna see some quick consequences of this next, where if you have a loop, then so long as you can freely homotope this loop to another loop, then the integral will also be the same. And so yeah. And also, if you have an open set that is simply connected, then we also have that any closed loop will integrate to 0, simply because you could contract it down to a point. Okay. So, all right, let's call that for now.